Museums all over America are sawing heads off one kind of dinosaur. It's just been realized the brontosaurs have been wearing the wrong ones for the past 100 years. For 150 million years, dinosaurs dominated the Earth. Then abruptly, they disappeared. Now, the mystery of why they vanished may have been solved. This is Gubbio, a medieval town in northern Italy. It's here that the clue was found. Geologist Walter Alvarez noticed a curious layer of clay in the rocks. The clay led Walter and his father, Nobel Prize-winning physicist Louis Alvarez, on an unexpected journey. Together with nuclear chemist Frank Asaro and his colleague Helen Michael, they uncovered an extraordinary story. It tells of events 65 million years ago, when a cosmic catastrophe may have devastated the Earth.
This is a good place to hunt for dinosaurs because we're right at the top of the Jurassic here. The Jurassic had a variety of both plant and meat-eating dinosaurs. We had Diplodocus, Brontosaurus, Apatosaurus, armored dinosaur, one kind of armored dinosaur, Stegosaurus. And now we've left the Jurassic. We're climbing up into the Cretaceous. And instantly, the dinosaur forms change. This is an excellent place to find something which might well prove to be an unknown little page of time in Earth history.
Jim Jensen is a dinosaur hunter. His favorite hunting grounds are deep in the hills of western Colorado. Here at Dry Mesa Quarry, the Jurassic rocks were formed 140 million years ago, right in the middle of the age of dinosaurs.
Sure you're not cutting that under too much?
No, I'm not.
Well, let's see. If you get that right there, maybe you can take this edge off over here.
Okay.
Right on that side. It looks pretty good. We put the mud, you can put it down to about right here.
Okay.
That should pick it off pretty good. I think there's a cleavage right in here.
Jim's been digging this site for the past 8 years. This giant neck vertebrae is just one of his recent finds.
It's pretty hard. Short time after opening the quarry this spring, we discovered this 5-foot length of bone here. It's about 6 inches wide, doesn't taper. It rather puzzled me at the time as to what it might be. Obviously, it was a rib, but off from what, I don't know. Down this area, we came across a large bone that comes out of the pelvis. It's one of the 2 paired bones which project downward between the hind leg. It's the pubis, very large. As we went around this end of the pubis, we came on the other half of the rib. This piece is 6 feet long. When joined to the other one, it makes the rib 11 feet long. Now, if you were to place this in life, imagine it in life, or let's just suspend these bones in air. There's this 4.5-foot vertebrae up there. It's the top of it's nearly 20 feet off the ground, and we have these 11-foot ribs hanging down here. You see these 11-foot ribs then have below them the belly coming down, making a cavity in there, something like 15 feet high, you see. If you're having lunch in there, you'd have to get on a stepladder to change the light globe. 2 ought to do it on this. That's got it now.
The bones are covered with canvas and plaster to protect them before they are removed from the ground.
You want to keep her not too fast. Not too fast, but once she gets going, keep her rolling clear over. There. Good, good. Fine. Now we can peel this bottom off here and mud and plaster it so that you have it secure.
After 20 years of digging, Jim's still excited when he finds something new.
See here, we're looking at the center part here. That's the bottom of that vertebrae you saw a while ago. Now, imagine that as I move this clod, the first sunlight will fall on that spot in 140 million years. You see right there? That's been in the dark for 140 million years, and here we're seeing it for the first time. Look over here, see? Look at that. Now, we leave the rest of this matrix here because that's a good pad to hold it, and we'll put mud, plaster, and burlap over this. We'll be ready to go back to the laboratory. And now, instead of weighing 400 or 500 pounds, this block will only weigh about 300.
Jim is the latest in a long line of dinosaur hunters who have scoured these hills. The heyday for dinosaur hunting was 100 years ago. Expeditions headed west, financed by the great museums of the East. In just 20 years, 100 dinosaurs were found. Competition for these bones was fierce, and inevitably, mistakes occurred. One of the greatest collectors was Othniel Marsh, head of the Peabody Museum at Yale. In 1879, one of his expeditions uncovered the bones of the very first brontosaur. It was a remarkable specimen. All it lacked was a head. That did not deter Marsh. He stuck on one he'd found 400 miles away. And that's the way all brontosaurs have appeared until now. Marsh had guessed, but he guessed wrong. So at museums like the Field Museum in Chicago, a series of face-saving operations are underway. The changes are necessary because these long-necked dinosaurs come in two quite different kinds. And while brontosaur's body belongs to one group, its head belongs to the other. The controversy about how brontosaurs should look isn't new. It started in the 1920s, when this quite different head was found. The Carnegie Museum in Pittsburgh sent out collectors to search for new dinosaurs. One of these expeditions found a brontosaur, and this time it had a head. The discovery delighted the expedition leader, Walter Holland, in the dark suit here. But an argument broke out when Henry Osborn, the acknowledged expert on brontosaurs, told him the new head was wrong and should not be used. Holland wasn't convinced. When he mounted the brontosaur in his museum, he left it without any head at all. After he retired, an old-style head was slipped quietly into place. Yet Holland was right after all, and Marsh's heads are beginning to disappear. Just 100 years after they were first discovered, brontosaurs are finally assuming their proper appearance. And if they seem to appreciate the joke, it's doubtful if their discoverer, Othniel Marsh, would have been quite so amused. Even today, guessing what dinosaurs were like is a hazardous business.
About a foot. Okay. Wait till I see it, wait. I'll tighten this up. Okay, come ahead.
This is one of the giant bones from Dry Mesa Quarry.
Is that going to clear there? Okay. All right, looks like it's going to make it.
To Jim's expert eye, it reveals a lot about what the animal was like.
Now, in life, this is the humerus, this bone here. This is the elbow. The upper end is the shoulder. And in life, this would be the left arm. And it would be about this high above the floor. And from here extends downward the radius ulna with the foot on the bottom. This animal would weigh about 50 tons and would stand about 45 feet to the top of its head from the floor.
This was the ultimate dinosaur. Called Ultrasaurus by Jim, it's the largest skeleton ever found. It was a giant cousin of the brontosaur, but the details of its life are as yet unknown. When more complete skeletons have been found, vivid pictures can be drawn of the lives their owners led.
Stegosaurus represents the armored dinosaurs. One of the most unusual features about Stegosaurus is the set of plates running down the ridge of its spine. Some people think these plates were to disperse heat or to collect it, and others feel it was used as a defense device. I rather doubt this because there were blood vessels like this, suggesting that they had a skin on the outside. If they were used for defensive purposes and had a skin on the outside, the skin would get knocked off every time they smashed into something. So I rather favor the notion that they were to disperse heat. The Stegosaurus had a small skull, little bitty brain. One of the terminal decorations here, which may have had a good function, was a double set of spikes. These spikes wouldn't disperse very much heat, but they may have been used defensively. Some artists show them being slammed into the breadbasket of some aggressor who was so unwise as to take a nip out of Stegosaurus as he was complacently munching on grass.
Stegosaurus may have been placid. Other dinosaurs led more energetic lives.
Well, Ornithomimus represents a little bipedal dinosaur, bird-like dinosaur. Its hands were used for feeding, not for grasping other creatures, because it was not a carnivore. Tail was used as a counterbalance and carried itself very much like an ostrich. A rather pleasant-looking eye. It was not an aggressor. Had very strong hind legs, 3 toes, large muscles in the hips here, and was capable of a great deal of speed. I think the stride on Ornithomimus would be something like 12 feet, so when it was out and running, it could cover the ground fairly rapidly. Tyrannosaurus is the most famous of all dinosaurs, a terrible meat eater, and the thing that makes it so fascinating to people is the mouth. The mouth. It had a very large skull, the largest of all the carnivores, and could eat an average-sized person in one big gulp. Make an evil-looking eye here. And could creature made a living by tearing apart its neighbors. And its hind feet were used for more than just walking. And besides being used for locomotion, was no doubt used to hold the victims down. And so it had claws here that not only served for walking, but also for holding the victim down. But also could probably slap its victims around as crocodiles do with their tails, and no doubt could flatten a horse with just a medium twitch. The most important tools Tyrannosaurus had were the long scimitar-like teeth. These were curved, not all the same length, and had serrate or saw edges on them. Those saw edges enabled it to rip through its victim's flesh. And when these teeth wore out, they fell out and were replaced by new sharp teeth.
Life must have been hazardous around tyrannosaurs, although being big probably helped brontosaurs survive. The reign of dinosaurs lasted 150 million years. Then, at the end of the Cretaceous period, they all disappeared. When the dinosaurs died out, so did the flying reptiles, the pterosaurs. All the giant marine reptiles, like the plesiosaurs, vanished too. When the last dinosaur vanished, the Earth must have seemed an empty place. This is Gubbio in central Italy. A deep limestone gorge behind the town records the extinction of millions of tinier creatures too. Geologist Walter Alvarez knew these rocks were interesting, but he did not suspect what a curious story they concealed.
One of the aspects of Earth history that's very well recorded in these limestones near Gubbio has to do with the evolutionary development of the forams, little single-celled organisms that lived in the surface water and whose shells are very abundant in these limestones. The evolutionary development of the forams has been studied for years by the Italian paleontologist Isabella Premoli Silva. What she found is that beginning way back in that direction, down section and back in time, there's about an 800-foot sequence of layers, and every piece of rock that you break open is full of forams. They are from the time interval that we call the Upper Cretaceous, and they show a very gradual, slow sequence of evolutionary changes. This is the top bed of the Cretaceous, this white one right here, and if you look at that, it's full of the same old Cretaceous forams, just like all the rest. Then there's about a ½ inch of clay right here. Let me get it out and show it to you. It's a reddish clay, sometimes parts of it are gray. It's completely different from the limestones. So there's about a ½ inch of that, and because it's entirely clay, it doesn't have any of the forams in it. Then we go to the very next bed, and you see something that's completely different. when you look at this limestone bed with a hand lens, you just can't see any forams at all, although the ones in the Cretaceous are very easily visible even to the naked eye. It looks like there aren't any, but when Isabella studied it under the microscope, she found that it's just crammed with very tiny forams. Then, if you go up section from there and follow the subsequent evolutionary history of this little foram, which seems to have been the only survivor of the extinction at the end of the Cretaceous, you'll see that it evolves into a whole variety of new species which fill all the evolutionary niches that were left vacant when the Cretaceous forams died out. So this clay layer right here marks the boundary between two different geological periods.
The clay turned out to be more than a convenient marker for geologists. Its presence, just at the boundary, was puzzling. And when the clay layer attracted the attention of Walter's father, Louis Alvarez, an extraordinary story began to unfold.
About 3 years ago, Walt came in with this piece of rock that he'd brought home from Italy, and I asked him to explain it to me, and he said, well, at this particular time, about 50% of all of the living creatures on the Earth disappeared. So he said, what we think is that for some period of time, the limestone-making mechanism is turned off, and we don't know why. It's just turned off. And during that time, the clay keeps coming down, and so we have clay that's free of limestone. And then, for some reason, again, we don't understand, the limestone-making mechanism is turned on, and so then you go back into the tertiary limestone. And I said, gee, Walt, that's about the most exciting thing I've ever seen in my life. Let's see if we can't find out how long it took. I said, do you really not have any idea? He said, well, if you take the normal rates of sedimentation, it's probably about 5,000 years, but we really don't know. So I said, well, I'll go home and see if I can think of some way that we might learn how long that clay layer took to deposit.
Louis came up with an ingenious idea: measure how much cosmic dust the clay contained. Louis knew the solar system is filled with fine dust, the remnants of the gigantic cloud out of which the sun and planets first condensed. Most of the dust was swept up by the young Earth as it formed. But even today, 100,000 tons rains down on the Earth every year. Louis realized that if the clay layer had taken a long time to form, a lot of dust would have fallen and mixed with the clay. The dust could be detected because of unusual elements like platinum and iridium which it contained.
And I plugged the numbers in, and they looked pretty good. And I looked up the nuclear properties of the various platinum group elements, and it was obvious that iridium was the one to go after. It was much, much easier to detect than platinum or osmium or any of the other such elements. So I told Walt about this. I said, this may give us an answer to how long it took to deposit the clay.
That's not quite how things turned out. Louis asked his colleagues at Berkeley, Helen Michael and Frank Osaro, to measure the iridium level in the clay. A lot of iridium should mean the clay had taken a long time to form. If the clay had formed quickly, it should contain much less. Either way, the iridium would not be easy to detect. It would be present in tiny amounts, mixed together with the dozens of other elements the clay contained. To measure it, an exquisitely sensitive technique called neutron activation analysis had to be employed. So carefully prepared samples of clay were taken down to Berkeley's nuclear reactor. Here, the samples were bombarded with neutrons produced in the reactor's core. The neutrons excite the atoms in the clay. Later, as the atoms decay, they give off gamma rays. The pattern of gamma rays reveals which elements are present. Frank Osaro.
This is a gamma ray spectrum of an irradiated sample from the Gubbio boundary layer. The gamma rays here, several dozen in number, represent approximately 20 to 30 different elements. The one that we use for the iridium analysis, you can't detect because it's too small. It appears where you see the small light. And if we expand the scale, you'll be able to detect it. Now the scale has been expanded and it's still a logarithm plot, which means that the peak is hard to see. By changing to a linear plot, the peak stands up above the background. This larger peak is due to another element, europium.
The results surprised everyone. Iridium was found in large amounts, much more than the cosmic dust could explain.
What we did find was a huge increase of about a factor of 30. Now, there was no way that we knew of that we could explain such an increase by conventional terrestrial chemistry or geochemistry.
Louis was puzzled too.
Well, I couldn't imagine what could have produced such a high concentration of iridium, but after all, that didn't bother me because I'm not a geologist. Walt couldn't imagine what had done it either. But when Helen and Frank came in with the other 28 elements, then it was clear that the iridium had to have come from outside the Earth.
Louis realized they'd stumbled upon an important clue. But what did it mean?
While Walt was in Italy and Helen and Frank were making measurements, I sat in this chair here for about 6 or 8 weeks, reading books on astrophysics and trying to understand what could have brought in the iridium and also killed the animals. And I went through a lot of scenarios. Some of them were so wild I wouldn't even dare mention what they were, but I remember thinking at the time each of them looked pretty good.
He would come up with them. These would be talked about, evaluated with respect to how well they agreed with what was known of the physics of the situation, and discarded. After about a month and a half, he came up with one that none of us could knock down, and that's the one that we're working on now.
Well, if you take an asteroid that's about 6 miles in diameter and have it bump into the Earth, it will vaporize itself and also vaporize perhaps 50 times as much crustal material, and that will be thrown up high. Some of it will go into low Earth orbits. Some of it will be turned into dust. Much of it will eventually end up as dust in the stratosphere and be spread worldwide. And it will block out the light, and that's the key. It's the blockage of the light that kills the plants, that kills the phytoplankton that sits on the surface of the ocean and that feeds the fish and now, of course, feeds the whales. All of that dies for lack of sunlight, so the food chains are disrupted, the animals die of starvation.
The world laid waste by a cosmic collision. Such catastrophes do occur. Geologist Gene Shoemaker.
This is Meteor Crater, Arizona. It was discovered thousands of years ago by the Native Americans that first came to this part of the world, and was then noticed by the sheep herders who came to this area in about 1880. The crater is about 4,000 feet from rim to rim, and about 600 feet deep from the highest points of the rim down to the crater floor. In about 1890, meteorites were first reported in the scientific literature from this location. And that report led a geologist, G.K. Gilbert, to come and see the crater, and he came with the intent of proving that the crater was of impact origin. He went away disappointed with his proofs, however, and concluded that the crater was actually formed by an eruption of steam, perhaps produced by volcanism, which is a phenomenon abundant in this area.
The origin of the crater remained a mystery until Gene Shoemaker provided the evidence about how it had been formed.
One of the essential features of the geology of this crater is the uplift of the bedrock and the deformation and tilting of the rocks in the walls. In addition to being lifted, the rocks have been shoved back away from the center of the crater by hundreds of feet as well. In fact, they were shoved back by the shock wave which opened the hole, the shock produced by the impact of the meteorite. So this deformation is one of the clues by which we identify a meteorite crater. Another clue to the origin of the crater lies in the way in which the rock debris thrown out landed on the outer rim. Let's look across the crater wall where we can see the debris layer itself on the horizon. Below that, a dark red layer of rock, and then under that, a brown-stained layer of rock forming the cliff. And finally, beneath the talus and broken rocks fallen from the cliff, and not exposed to our view, is a very thick unit of white sandstone.
It's the way these layers have been rearranged in the crater rim that is so revealing.
Here's the layer of red sandstone that we could see in the distance high in the crater wall. And just at my hand level, and on a sloping surface that parallels the beds below, was the original ground surface, which has now been tilted up. And above this contact, we see a layer of red sandstone debris that can be traced over through this cut, and it makes a layer about 2 or 3 feet thick as we look at it. The debris here came from the rocks immediately below. Above the red debris layer, we have a second layer starting at this point, made up of fragments of limestone, and the top of the limestone occurs right here. So that this is a layer now made of limestone debris which came from the next formation below in the bedrock. Finally, there's a thick layer of white sandstone which extends from here to the top of the cut. So when we look at this debris in detail, what we find is that it is made up of pieces of the bedrock which has been lifted out of the crater and laid back as a great flap and dumped upside down on the surrounding rim, preserving the sequence of strata that we saw in the bedrock, but in inverted sequence. And it's this upside down stratigraphy or inverted sequence that is characteristic of impact craters.
Meteor Crater was formed when a rather small meteorite landed. There are objects that can make much bigger holes. This is Mount Palomar Observatory. Dr. Eleanor Helene comes here 4 nights each month to search for some very curious objects. She is interested in a special kind of asteroid, those with orbits that bring them alarmingly close to the Earth. The asteroids Dr. Helene studies are called Apollo objects. They are tiny rocky planets, 1 to 10 miles across. The very first Apollo was discovered in 1932, and since then, more than 30 have been found. Finding these asteroids isn't easy. It's impossible to predict when they will pass by, and they are no brighter than the faintest star. If you could see one with the naked eye, this is how it might appear. Each night, dozens of long exposure photographs are taken and developed. Hundreds of plates may have to be examined before a single asteroid is found. When the plates were exposed, the telescope followed the motion of the stars. Stars appear as points of light, but an asteroid moving through them shows up as a tiny streak. So how many more of these asteroids are there, Dr. Helene?
Our estimate of the population of these near-Earth asteroids is around 1,000, perhaps plus or minus 50%. So we're dealing with a population perhaps of about 1,000 to 2,000 Apollo asteroids.
1,000 asteroids in our region of space. Most are in unstable orbits. It's just a matter of time before one collides with the Earth. But where do they come from? Why are they here? One theory suggests they come from the asteroid belt in the region of space beyond Mars. They may be tossed out of orbit by Jupiter's immense gravitational field. What happens when an asteroid arrives?
Picture yourself standing about 20 miles from here, about 25,000 years ago. Out of the southeast, a nickel iron asteroid about 150 feet across is approaching the Earth. As it plunges into the atmosphere, it forms a brilliant meteor which grows brighter and brighter and becomes finally much brighter than the sun. In fact, it grows so bright that you will be on the verge of being scorched. You will want to take off your shirt and throw it on the ground. At that point, the meteorite strikes the ground, and it sends a shock wave with pressures of millions of atmospheres down into the rock and back up into the meteorite. The meteorite burrows into the ground like a hydraulic jet, forcing the rock aside, flattening, and then being deflected and thrown back out again. So from the moment that the meteorite strikes, a spray of shock-melted meteorite and vaporized meteorite and melted and vaporized rock squirts out at high velocity, a velocity of several miles per second. The spray continues to rise, and it forms a plume that grows bigger and bigger and bigger. Finally, the plume becomes about 4,000 feet across at the base, And by that time, the top of the plume of material ejected is extending many miles up into the atmosphere. In fact, most of the atmosphere has been blown away, having been pushed away by the shock wave made by the meteorite. The first thing that will happen to you after being nearly scorched is that you will hear the shock wave in the atmosphere itself, and it will come like an enormous clap of thunder. In fact, it will be strong enough nearly to bowl you over, even at 20 miles. The plume, meanwhile, continues to grow and finally just evolves into an enormous black cloud of dust, which will punch up through the atmosphere like a typical mushroom cloud from a nuclear explosion.
Now, it was too complicated for me to be able to calculate what would happen to this dust that was thrown up into the air. But fortunately, I had this rather rare book that was put out by the Royal Society concerning the eruption of Krakatoa. Krakatoa was a mountain that blew up in the Dutch East Indies in 1883 and spewed lots of dust into the atmosphere. My father had bought this book a good many years ago. I had then given the book to Walt when he became a geologist, and now he was in Italy, and I had to get the person in his home to let me in and lend me the book. And when I got it, it turned out to be an absolute gold mine. For example, I found out how many cubic miles of the island had blown up, how many cubic miles of dust stayed up in the stratosphere, and for how long. The dusty sunsets, which were seen worldwide, lasted for 2 to 2.5 years. And it also gives the physics as to why the dust stayed up that long, and that's a brand of physics that I know something about, so I believed it. We don't know how long our supposed cloud would stay up, but we've always said a few years or several years. It would certainly be longer than the 2.5 years, but not probably as long as 5.
When the dust cleared, the Earth would have become a bare and barren place. It's a dramatic story, but is it true? Were plants wiped out along with the dinosaurs? Here in northern Wyoming, the rocks still preserve a record of the plants that were growing 65 million years ago. Paleobotanist Leo Hickey.
Today, this area is a virtual desert. Less than 6 inches of rain a year here. Climate subject to extremes of temperature. 100-degree days, not unusual at all during the summer. 20 below, not unusual at all in the winter. Yet we know from the evidence of the rocks, the pollen, the animals and other plants that we find, that during the age of the dinosaurs, this area supported a lush subtropical forest growing on a lowland floodplain with meandering streams traversing the plain.
The fossils found here are early tertiary. They are from plants that were growing just after dinosaurs vanished at the end of the Cretaceous period.
Chip this away. This may be something very new. There it goes, I think. Look at that.
Wow.
Now that's not bad.
That's beautiful.
That's really something. It looks like it may be a member of the laurel family. Oh, what do you have there? Cissus marginatus. This is a very interesting form. It's one that hasn't left any descendants at all in the modern flora. In fact, we don't even know whether this one is a shrub or a tree. Don't know anything about it, other than the fact that persists out of the Cretaceous and dies out about this time in the early Tertiary.
Leo, what's this?
Oh, okay, Scott. That's a Japanese scholar tree, the ancestor of it. Another very important genus in the Cretaceous and also in the early Tertiary. This is very, very similar to the ones that grew in the Cretaceous, much more so than the ones in the later part of the Tertiary.
Each fossil found here is compared with ones from the Cretaceous era. A picture is built up of the plants that died out and those that survived.
By excavating a number of these pits, a large number, we were able to reconstruct the vegetation. And as we do so, as we look at the vegetation of the early Tertiary, we find that in these earliest pits that are just a shade above the Cretaceous, we're really still dealing with the Cretaceous flora. It's an attenuated Cretaceous flora, to be sure. About 50% of the forms that characterize the Cretaceous are extinct, but the basic plant communities that characterize the Cretaceous and the dominant plants within those communities remain the same.
There is a significant pattern to the changes that occurred. All these plants became extinct. Most of them are tropical forms. These temperate plants, by contrast, are the ones that survived.
Another thing that we see across the Cretaceous-Tertiary boundary is a rather significant decrease in the total diversity of the flora. Again, tropical and subtropical floras tend to be more diverse than temperate floras as a whole. So that we regard all of these evidences as consistent with looking at this flora as representing or growing during a period of climatic cooling.
So where is the devastation an asteroid would have produced? Leo Hickey doubts it actually occurred.
Looking at the plant evidence across the Cretaceous-Tertiary boundary here, we see no evidence of an asteroid impact.
Was it a hit or a miss? Plants leave the question unresolved. There is a second problem facing the theory. Where did the asteroid land? The moon has ample evidence of such impacts. It is covered with craters. The asteroid that hit the Earth would have made a crater more than 100 miles across, 4 times the size of this one on the moon. On the Earth, craters are much harder to find. We live on a planet with very active geology. Craters are quickly eroded away. But some of them do leave traces behind. And about 200 impact sites have now been identified. Yet the problem with the asteroid remains. None of the craters are the right size or age to have resulted from its impact. One other alternative exists. The asteroid may have landed in the sea. That might have produced some unexpected results, as astronomer Fred Whipple suggests.
Now, if a 10-kilometer asteroid should plunge into the ocean at 15 kilometers per second, it wouldn't really notice the water very much unless it fell into one of the deepest deeps of the ocean. It should make a crater perhaps about the size of my thumb. But we don't find any such craters in the ordinary ocean. And I don't think we really should expect to find them for the reason that the waves, water being exploded away, would come crashing back in again and carry with it much of the ocean material. And then the Earth, of course, is not completely rigid, and the wound should heal up, and that accounts for the fact that we don't see any such crater in the normal ocean bed.
But what if the asteroid landed on a mid-ocean ridge where the continental plates are pulling apart and the Earth's crust is very thin? What would have happened then?
It would have punctured that thin, fragile crust and buried itself perhaps 30 to 50 kilometers below the surface, tapping this reservoir of upwelling lava, which has been spreading the continents apart for much over 100 million years. The result would be, of course, a colossal volcano. And that would be active for millions of years, keep bringing up material, and create a landmass. So what we should look for is not a crater, but a landmass, a strata continental ridge.
Huge quantities of molten rock would ooze out from deep inside the Earth. As the rock cooled, a brand new piece of land would have formed.
So with this idea in mind, I looked over all the oceanic ridges on the entire Earth and found that there was only one landmass astride an oceanic ridge, namely Iceland, right in the middle. So with great temerity, I asked the geologists how old Iceland was, and they said about 50 or 60 million years, which was just the right answer. So that gave me some encouragement. And then there was another point that added a little weight to the idea. The amount of iridium that was measured in these strata between the two geological eras. And as iridium was measured in Denmark, in Italy, and in New Zealand. And the exciting result was that the lowest reading was in New Zealand, somewhat more in Italy, and very much more in Denmark, which is closest to Iceland, suggesting that the fall was up in this region somewhere, and possibly that the hypothesis is right, that the great asteroid that extinguished the dinosaurs actually may have fallen and produced Iceland.
These ideas about the end of dinosaurs still need proving, yet even now they are having an unforeseen effect. They are drawing attention to a threat that hangs over us all. Gene Shoemaker.
Well, what happened here will happen again. About every 100 years, an object encounters the Earth with enough energy to make a crater like this one if it didn't break up in the atmosphere. The last time that happened was in 1908, and a body broke up over Siberia. Had that hit the ground, it would have made a crater as big as this one. In this case, we got a crater because the meteorite was iron. Usually the meteorites are stone, and they have to be about 3 times as big in order to come all the way down and hit the ground. Such a body will actually hit the ground and make a crater about 3 miles across about every few thousand years. What we have to do to prevent these catastrophes now is to mount a careful survey of the sky to discover the objects which might collide. And then, of course, it's going to take some effort from NASA and the space program to get out there and implant those explosives, which by producing a small cratering event will budge the asteroid in its orbit just enough. You only have to change the velocity by a tiny fraction of an inch per second to make it miss the Earth if you do the maneuver about 3 years ahead of time.
There is an air of science fiction to this tale, linking as it does two unlikely partners, the asteroid and the dinosaur. Yet it's also an example of one of the best kinds of scientific inquiry. When these scientists from Berkeley started, they didn't know where their investigation might lead. They simply asked questions and then listened thoughtfully to the answers they received.
What Walt and I proposed to Helen and Frank was a very simple thing. It really wasn't very important. It was just a way of getting our foot in the door let's make a measurement and see what the sedimentation rate was. Turns out that that was not what we did. It's the most exciting kind of science. In fact, there's even a word for it, serendipity, I'm sure you know. It means you're not looking for it and you stumble on it. But you have to be there with your eyes open and recognize that you have something really strange when you see it. So it's not all luck.
The material on this video cassette is protected by copyright. It is for private use only, and any other use, including copying, reproducing, or performance in public, in whole or in part, is prohibited by law.